Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and a very good morning or greeting to everyone in whatever condition you have on in whatever day, either daylights or during night time. I hope you guys are doing fine. Today we will learn into our next chapter, which is the chromatography. Before we are going further into the liquid chromatography and also the gas chromatography method, let's go into the basic principle of chromatography method, so you guys can understand the concept of liquid chromatography and also gas chromatography better. So let's go back to the basic principle of the chromatography. Okay, I believe this is not the slide. Really sorry. Okay, here is your slide. Okay, so chapter 2, liquid chromatography, part 1. Before we going further, let's go back to introduction to chromatography. Okay, here is the course outline, so many things, very specific. I believe the definition. Yeah, it is definitely the definition. First thing first, we will look into the definition. Okay, then we will look into the principles. After we know the basic principle, we will try to learn about the interaction of the chromatography, and then we will look into a little bit of the application of chromatography, especially in forensic science, and then we will learn about the chromatography techniques available. What is the chromatographic definitions? Why chromatography definition is over there? Am I wrong? Oh yeah, sorry. The definitions over there is mean the specific terms. Definition. Okay. Right. Effect of sensitivity and selectivity on resolution of the separation. We will learn about the peak asymmetry as well. Okay, what is peak asymmetry? Is like this. Sorry, I'm not good with drawing. Where's my eraser? Okay, I'm not very good with drawing. We want to know either the peak is symmetry or is little bit tailing. Okay, this is mean by peak asymmetry. Then we will learn about the peak broadening. Either it is sharp or it is broad, or maybe it is sharp or it is broad. Then how we can improve the resolution in chromatography separation. How we can improve from this situation to get a very sharp peak, from the peak broadening to have a sharp peak. We will try to look into that as well. And then general factors in increasing the resolution is about the same. And then how can you present or discuss your result? We will look a little bit about that. Okay, I think it's very important if you are doing the analytical instrumentation or chemistry analysis during your dissertation. So I believe the information will benefit you guys a lot. And then we will learn about the type of calibration methods available, and definitely you will use this during your practical as well in your dissertation if you are doing instrumentation analysis. Okay, so basically here is the course outline of this introduction of to chromatography. So we have a lot, so let's move. So I don't want to waste any more times to explain the course outline. Just let's go to uh, the topic. Okay, let's go to the definition of chromatography. Chromatography originated from the Greek words. Chroma means color. Okay, we have the first part, the chroma, and then we have the graphy, means writing. So it means color writing. For example, you want to write the color of rainbow, so you want to separate the color of the rainbow. In the chromatography, is a technique for separating mixture into their components in order to analyze, identify, purify, and quantify. Okay, here is the keywords of the chromatography technique. The first one, we need to define where it's come from actually, the chromatography. It comes from Greek words. Chroma means color, graphy means writing. And then what is the purpose of the chromatography? Chromatography is a technique for separating mixtures into their components in order to analyze, identify, purify, or quantify. Okay, so we have the mixture here. So we need to write their color into components. Okay, that is why we call as the chromatography. So we have the mixture. So we want to write or we want to separate into its components. Okay, for example, we have the red one, blue one, the dot one, and the yellow one. So by doing the chromatography, we can separate on its components in order to analyze, to identify, to purify, or to quantify. Analyze is general for these three. Okay, if I can say that analyze is as a whole, identify is in the system, quantify is in the system. Okay, all right. Identify that we want to know exactly what is the yellow one, what is the red one, what is the blue one, what is the dot one. Or for the purification, for example, in the mixture, we want to only to isolate the yellow one. So we want to remove the other three. So we extract, we separate the yellow one, we collect the yellow one, and then we remove the other three. So that is what it's meant by purify. Okay. For quantify, we want to know, for example, how many yellow is it inside of in our sample, how many red in our sample, how many blue or how many dot in our sample. So when when we talk about the quantify, we always look into the how much the quantity of certain or analyte of interest. Okay, certain compound or analyte of interest. Okay, so here is the definition of chromatography. I believe this kind of question of definition is one of the most popular one. Okay. So we have learned about the definition of chromatography. Okay. Next, we will look into the principle of the chromatography. How chromatography works. In chromatography, we have two phases contributed to separation of our mixture. The two important phases is a stationary phase and a mobile phase. Stationary phase is mean that the phase that will not move during the process of separation. It will be static on its path. On the mobile phase, it's moving. The mobile phase is the one that will move the analytes along the stationary phase in order to separate the components. Okay. If you look in the illustration, okay, we have the mixture of sample and then we have the packing material. The packing material of this column, this is what we call column. Okay, we have the injector over here, we have the detector. The first we inject our mixture. Inside of the column here, we have the packing material that we call as the stationary phase. Stationary phase, the phase that will not move and it will static on its own phase or location. So we have the mobile phase that will move the mixture. Okay, and the mixture will have the interaction with the packing material. During its interaction with the packing material, so the components will start to separate based on its own characteristic or its own properties. Or we can call on its own adsorption or absorption. Okay, the mobile phase will flow continuously across the stationary phase. Okay, this is how we can understand the principle of the chromatography. The compound is separated or distributing themselves between two phases, mobile phase and stationary phase. Okay. These two components is very important to separate the mixture. Okay. The stationary phase can be a solid packed into a column. Okay, solid packed into a column, for example, like here. Or if in the cross-sectional, we have the packing material, a small particle of packing material we stuck inside the column. This is a kind of solid packed material. A solid, and then we have a next stationary phase. It can be a solid coating the surface of a flat plane material. For example, for a TLC or thin layer chromatography, okay, in a sheet of steel, they have the particle on the surface. Okay, we will learn about that later on. Or a solid can be inside a wall as well. For example, so you have the capillary column, or we can call as the column. Inside the column, you can have the solid coating on the wall of the column. It can be like that as well. Or the next one, a liquid supported on a solid. Okay, it means, for example, if I can draw bigger, okay, we have the particle, and for each particle, they have the coating of liquid outside of the particle. Okay, that is one kind of idea. So we have a lot of particle, but outside of the particle, we have the liquid supported on solid. So liquid coated on the solid. So here it is, here it is, here it is, here it is. Okay. Or we can have a liquid supported on the inside wall of an open tube. Or we can have the thing like this. Okay, there is no solid particle, we only have the liquid support. So the liquid is support or coated on the wall of our column. Okay, so this is the one. Or for in this condition, this supposedly to be here, here. This one supposedly to be here. This one supposedly to be here. Okay. Alright. So I hope you guys can understand what the stationary phase can be look like. Okay, the next one, the mobile phase can be gas, a liquid or supercritical fluid. Okay, we can have three kind of mobile phase, but normally we always divide into the gas and liquid because the supercritical fluid also belong to under liquid mobile phase. Okay. Okay, I believe the same principles I already mentioned in the first few slides before this. The mixture is introduced into the stationary phase and the mobile phase. The mobile phase will carry out the components through it. Each individual of analytes, it means that like the purple one here, the green one here, and the blue one here, will interact with the two phases in the different manners. Okay. So the analyte that interact with the stationary phase the most, we will elute the last. The analyte that have the least interaction with the stationary phase will be eluted first. It means that the analytes love the stationary phase most, will attach to the stationary phase the most, and then they will elute the last. Again, when your analyte doesn't interact with the stationary phase, they don't love the stationary phase. They love more on the mobile phase. So they will elute the fastest. The interaction is the least. The least interaction with the stationary phase, the faster the analyte will be eluted. If we can draw the chromatogram over here, okay, we can have the tree one, okay. So here is for the blue one, because the component has the least interaction with the packing material. It loves the most of the mobile phase. The green one is the intermediate one, okay, and the purple one is the last one that will be eluted, because we have the detector, right? So again, we have the analytes of mixture over here. Okay, we have the during the injector, through the injector we introduce the analyte of mixture. The mobile phase, the one that brings our mixtures through the column, and then it will bring our analytes or the mixture until it reach the detector. The analyte that interact the most with the stationary phase will elute the last, or will reach the detector last. The analyte that has a least interaction with the stationary phase, or doesn't love the stationary phase, it will elute earlier. In this situation, the blue one will reach the detector first, or we can call eluted first. So in this situation, the first one is blue, the second one is green, and the third one is the purple one. Okay, analytes differ in their affinity for the stationary phase and also the mobile phase. Okay, if we have mixtures of analytes, they usually have a different affinity, or in the easier words, we can say that they have different preferences towards stationary phase or the mobile phase. Okay, each analyte exhibits different migration and elution patterns, and thus a mixture of analytes can be separated and quantified. Okay, so example, if you have the mixture of A, B, and C, they have different preferences with the mobile phase. Okay, we can imagine like this. Maybe Hassan love me more compared to Amy love me. So maybe Amy hate me. So Amy will elute earlier, because Amy doesn't attach to me stronger. But Hassan, the person that love me the more, that attached to me stronger, he will elute the last. Oh, that is kind of analogy that I can describe. So each analyte exhibits different migration and elution patterns. Okay, and this a mixture of analytes can be separated and quantified. Okay, as the analogy as I described before this. So the difference in their affinity can be affected by, in gas chromatography, is on the boiling point. Okay, for GC, for the gas chromatography. But for the liquid chromatography, it doesn't involve the boiling point. Okay, it will involve the polarity. Okay, it will involve the it can involve in the size exclusion, or maybe it can involve the electronegativity. This is the kind of example can affect the preferences of the analyte. Analyte, for example, for the boiling point, the analyte have the lowest boiling point will elute earlier compared to the analyte that have higher boiling point. So the analyte that have a lower boiling point, they can become easily to be volatilized, and then will easily to be flow with the mobile phase of gas. That is the kind of example. The tracing of the output signal vs time or mobile phase volume is called as the chromatogram. So signal versus time. Signal versus time. Okay, when we have the signal versus time, okay, and then we have the response over here, we call it as the chromatogram. Okay, let's go to the chromatography basis of interaction. We have 5 basic interaction of the separation. The first one, we have the partition, and then we will learn about the adsorption, and then we will learn on the affinity interaction before we go into the Ion Exchange, and then finally we will learn about the size exclusion of interaction. Okay, let's look into the first interaction of the chromatography. The first that we will learn today is on the partition chromatography. Partition chromatography referred to chromatography separation technique that involve two immiscible phases. If we read a book or we find in most of the references, they mention partition chromatography involve the separation between liquid-liquid separation. But in a modern kind of the separation technique today, the definition of partition chromatography is when the chromatography separation involve two immiscible phases. It can be liquid-liquid, liquid-liquid. It can be as well as the liquid gas. A liquid stationary phase is bonded to a solid surface. For example, in the gas chromatography column, we have wall-coated open tubular column. It means that the wall of the tubular column or capillary column, we have the liquid phase coated on the wall of the column. The solute equilibrates between stationary phase and the mobile phase, widely utilized in GC column. Okay, so what is meant by solute equilibrates? Solute is mean that all the mixture, including our analytes, for example, in the mixture, why my pen doesn't working? Is it habis battery? Oh, no, still there. Better if I draw you a bigger illustration. Okay, let's say you have your sample. You have the mixtures of triangle and circle and also the square. Okay. In the partition chromatography, as I mentioned before, we have two immiscible phases. It can be liquid-liquid. For example, we have liquid 1, we have liquid 2. Okay. The above layer is on the liquid 1 and the below layer is liquid 2. In the gas chromatography, for example, okay, this is the situation when the partition is involved two immiscible liquid. But on gas chromatography also has the partition chromatography when it's involved two immiscible phases of gas and liquid. For example, if I draw the column figure, on the column we have the what we call the liquid coated on the wall, or inside of the wall of the column, we have the liquid coated. Okay, how partition works? For example, we have the solute. Solute is mean that we have the mixture of analytes and also the things that we don't interest. Okay, except for sample matrix lah. Sample matrix is not included. That is what we call as solute. Okay, so if we are using the liquid phase in the partition, we do the separation. For example, we want to, our analyte of interest is triangle. So during the partition chromatography, during the extraction or chromatographic process, the triangle is separated into the other liquid layer, and the other one will absorb the others. Okay, that is the kind of the idea. Or maybe we can also say like this. Okay, we have these three as our analytes. We have these three as our analytes. Okay, here is the stationary phase. The liquid 2 is the stationary phase. The liquid 1 is our mobile phase. In the situation of the liquid chromatography, the mobile phase is liquid. For the stationary phase in here also liquid. For example, okay, let's say the triangle. Okay, the triangle is the one that not interact the most with the stationary phase, so it will always in the liquid one or in the mobile phase. For example, the circle. The circle, it can be either interact with one or with the stationary phase. So the interaction is quite moderate. Maybe in this situation, the square is interact with the most with the stationary phase of the liquid too. If we draw the chromatogram, which one will be eluted first in this situation? For example, if the liquid 2 is the stationary phase and the liquid 1 is the mobile phase. If in this situation, the first one that will be eluted is the triangle 1, because the triangle 1 is the one of the solute that not interact the most with the stationary phase, which is the liquid 2. For the circle, it will be in the middle, since it has the capability to interact with both phases, the liquid 2 and the liquid 1. For the square, because it loves the most of the stationary phase, or we can call here is the liquid 2, so it will elute the last. Okay, so if we look on the other side of the gas chromatography using the open tubular column, in this situation, for example, we have the square that love the most with the stationary phase, and we have the circle one that can moderately interact with the liquid phase over here, and the triangle that doesn't interact at all with the liquid stationary phase over here. So they will also show the same profile as if we look over here. So again, partition chromatography involves two immiscible phases. It can be liquid-liquid, it can be gas-liquid. But usually in the partition chromatography, the stationary phase must be liquid. Okay, again, I repeat, in the partition chromatography, the stationary phase supposedly, compulsorily must be liquid. Okay. The mobile phase can be either gas or can it be either liquid, but both of the gas and the liquid as the mobile phase must not be miscible. They must be immiscible. Before that, we can call this as the partition chromatography. Okay. If you Google or you find from the book, mostly they will say that partition chromatography is a liquid extraction techniques. But don't get confused, because it can also involve the gas and liquid as long it doesn't miscible. Okay, the other kind of the example of the partition chromatography when we are using the solid coated technique. It means in the column we have the particle, a lot of particle, and then we have the liquid coated on the surface of the particle. When it's involved, the liquid and also then the liquid is not miscible with the mobile phase, and also the analytes will interact in this situation. Okay, for example, the square one. Okay, this also is a type of the partition chromatography. So we have this kind of partition chromatography interaction. The example of the partition chromatography where we use the paper chromatography, we will learn about this. We will learn about paper chromatography when we learn about the thin layer chromatography. And then we can also have the wall coated open tubular column, GC, or we can call it, we can also solid coated open tubular column, okay, or liquid chromatography. This all type of the chromatography technique is a part of partition chromatography. The next one is the adsorption chromatography. Again, before we are going further, if you have any kind of question, you may ask anytime at the group WhatsApp of the class, so we can share the information with all our colleagues. Don't be afraid or shy. You can ask anytime. If you don't ask of what you don't understand, so at the end you are the one who will lose during the process of teaching and learning. For the adsorption chromatography, as the keyword of adsorption is mean the interaction is on the surface. The active site of the stationary phase interact with the functional group of the compounds to be separated by polar or non-polar interactions, van der Waals forces, and hydrophobic interactions. For example, molecules are retained by the interaction of their polar functional group with the surface functional groups. For example here, silanol and silica. Okay. Okay. We have this, if we can imagine the column, we have the solid particle. We have the solid particle. This solid particle is probably like this. If we using the microscopic technique, we can look maybe the structure like this, appear like this. So on the surface of the particle, they have the active sites, or maybe they attach the ligand over there to make the active site. So if we look over here, the analyte or the solute will interact with the active site of the solid or the particle, or we can call as the stationary phase. If we have the active site of polar, so the polar analytes will attach the non-polar analyte will not interact. If the active site is non-polar, for example, so non-polar analyte will attach greatly compared to the polar analyte. Polar analyte will elute first compared to the non-polar analyte. Okay, again, in the adsorption chromatography, the interaction is on the surface, where the surface active sites will interact with the functional group of the compound. Okay, the interaction can be polar, non-polar, van der Waals forces, or hydrophobic interaction. Again, if the active site is polar, the analyte that is polar will interact. The analyte that is least polar or non-polar will elute first. Okay, that analyte that is polar will elute the last because they interact the most with the surface. If the active site is non-polar, then non-polar analyte will interact the most. The polar analyte will not interact or will have a less interaction towards the active site, so they will elute the earlier. Okay, so this is the situation. If you have polar surface, okay, the chromatogram, the one that eluted earlier is non-polar. The one that eluted the last is polar because they interact the most with the polar surfaces or the polar active site. If in the surface we have the non-polar active site, so the non-polar the polar will elute earlier. The non-polar will elute the last because they interact the most with the surface of the particle or surface of the stationary phase. So if the keywords over here is the active site interact with the functional group, or the surface active site of the stationary phase interact with the functional group. So better I correct here. The surface active site, because absorption is the interaction on the surface. Okay. Better I make it black as well. Okay. Before we going further, in the partition chromatography, the interaction is between two immiscible phases, where the analyte must be interact with the liquid phase by absorption. A, B for the partition. Absorption. For the adsorption chromatography, the interaction with the surface active site of the stationary phase. So is adsorption on the surface only. The next one, we will learn about the affinity chromatography. Affinity chromatography is a method separating biochemical mixtures based on highly specific interaction such as that between antigen, antibody, enzyme and substrate, or receptor and ligand. Okay. Here we have the matrix we attach with the ligand, and then we immobilize the ligand. And then we have the sample to attach with our complex. And then we can remove the impurities. The one that will not immobilize or will not attach to the ligand, they will be eluted the first. Okay, so the one that attach to the ligand to form a complex, they will eluted the last. So in this situation, the impurities will eluted earlier compared to the sample that can attach to the ligand. Okay. So again, affinity chromatography is method of separating biochemical mixture based on the highly specific interaction such as antigen and antibody, enzyme and substrate or receptor and ligand. For the definition, if you cannot be able to remember everything, you just need to understand that you can understand. Okay, so I don't need you guys, for example, if the question appear, please describe affinity chromatography and adsorption chromatography. As long you be able to convince me with the correct understanding, so I will give a mark accordingly. I will give the mark accordingly. For example, like say you cannot remember a lot of things like here. You just write affinity is method of separating biochemical mixture via specific interaction. Okay, such as antigen and antibody. I think until that is also enough because antigen and antibody is specific interaction. Or maybe you just remember receptor and ligand, also will be accepted as the answer. Same goes to the partition chromatography, the interaction between two immiscible liquid. The example is using wall-coated open tubular column. Okay, when the analytes interact the most with the liquid stationary phase, they will elute the last. As long you can describe that as like that, I will give the mark. For example, in the adsorption, you said the interaction with the active site. Polar analyte will interact the most with the polar active site. Meanwhile, the non-polar analyte will not interact the most with the polar active site. So the non-polar analyte will elute earlier. As long you can show the understanding toward the interaction, I will give the mark accordingly. Don't worry about to remember everything as it is. You just need to write based on the understanding. That's why in the chromatography as well, in the analytical instrumentation, you need to understand. Don't try to memorize. Okay, the next one we will learn about the ion exchange chromatography. Ion exchange is specifically for ionic compound. Ionic compound is mean that compounds that contain negative charge or positive charge. For the ion exchange, we can divide into two. Depends on the charge of our analyte. The first one is anion exchange for analysis of analyte of an ion. Anion exchange is for anion. And then the next one we have the cation exchange. The cation exchange for analyte is cationic. Okay. Anionic is the compound with the negative charge. For the cationic is the something or the compound with the positive charge. Okay. Remember, the name of the exchange depends on the charge of the analyte, not on the charge of the bonded phase, or we can call stationary phase. In the anion exchange, the analyte is anion, negative charge. Okay. So to make it interact with the column, so the column must have a reverse charge or opposite charge. So the bonded phase or stationary phase must have a positive charge. So we can provide a better separation. For example of analyte that is anionic, for example is chloride, fluoride, okay, or what else? Fluoride, chloride, bromide, okay. That is example of the analyte which is anionic. For example of analyte which is cationic or has a positive charge, for example, is potassium, lithium, sodium, where their properties is positive. Okay, if you look over here, can you guess what kind of system, what kind of ion exchange is actually has been applied? If you look over here, okay, if you look over here, the bonded phase is positive. When the bonded phase is positive, it must be the analyte of interest is kinda negative, which is our analyte is anionic. When our analyte is anionic, then the system is for anion exchange. The application of ion exchange chromatography, the precise example is on ion chromatography or IC, ion chromatography. For example, in anion exchange of ion chromatography, okay, we will have the mobile phase that also anionic in nature. First, the anionic mobile phase will interact with the surface of the bonded phase. When you introduce the analyte, it will displace the analyte. For example, we have the analyte over here. It will displace the analyte. Okay, and then to elucidate the analyte over here, then the next mobile phase will displace the analyte. So this analyte will displace the analyte in the next resin or in the next phases. So the process is continuous until the analyte reaching the detector. Okay. So basically the ion exchange chromatography is for anionic compound, and anion exchange is for an ion analyte. Cation exchange is for cation analyte. The bonded phase has the opposite charge of the analyte of interest to make a separation better. Basically, the interaction is sample ion displace the mobile phase ion through the adsorption process, AD, adsorption. And then the sample ion is displaced by mobile phase. Okay, and then the sample ion will replace the next its mobile phase ion. Okay, the process is continuous until it's reaching the detector. Okay, the next one, we have the size exclusion chromatography. The other name of the size exclusion chromatography we can call as the molecular sieve chromatography. It's a chromatography method in which molecules in solution are separated by their size, and in some cases, molecular weight. Okay, if you look over here, this is the stationary phase with, they have the what we call have the pore. Okay, we have the pore size. Okay, so the analyte with a smaller size will go deeper inside the pore. Okay, meanwhile the analyte that is so big will not be absorbed or will not be attracted or will not be entering the pore size since it's too big. So what happens is the analyte that is the smaller the analyte, they will enter the pore size deeper. So they will interact with the stationary phase much longer compared to the one with the analyte which is the large size. Okay, if we look over here again, the analyte, the blue one is elute earlier since it is the biggest among of the analytes. The number one, which is the smallest one, will elute much longer because it is the smallest among the analytes. It is interacted deep inside the pore size compared to the other. Therefore, the number one has the more interaction to stationary phase compared to the others, especially the number 3. Okay, this is what we call size exclusion chromatography. Okay, let's go for the summary to the basis of interaction. Okay, the first pillar is the partition chromatography, separating it based on the solute partitioning between two liquid phases, or it's not necessary two liquid phases, it can be two immiscible phases. for example, gas and liquid. So it's not necessarily two liquid phases, but most popularly known among two liquid phases, two immiscible liquid phases. Okay. In the ion exchange chromatography, the separation is based on the ionic interaction between the surface and the eluents. And then we have the adsorption, the interaction between the surface of the stationary phase. And then the final one, we have the size exclusion chromatography, where the separation is based on the molecular size. The smaller the molecule, the more longer it will be retained. The larger it is, the least it will be retained by the stationary phase. If you talk to me which one is better, so it depends on the application. It's not necessarily one thing is better compared to the others. For example, for the ion exchange only allowed for ionic compound, but not for it's not what we call useful for analysis of a non-ionic compound. Okay, for the partition chromatography, it can help to have a better separation because the interaction with the stationary phase will be much more deeper compared to the one with the adsorption, because the adsorption in the surface. But of course, if you are using the partition chromatography, it will take much longer time of analysis. If your analyte is not that much, only one or two, so you can go for the adsorption chromatography. Okay. If your analytes, the absorptivity or the characteristic is about the same, you can try to proceed by using size exclusion chromatography. Okay, what is the application of chromatography? There is a lot application of chromatography. In pharmaceutical company, determine amount of each chemical found in the product. For example, in hospital, to detect blood or alcohol levels in patient bloodstream. In law enforcement, to compare a sample found at the crime scene to sample from a suspect. So this is the one that directly related to you guys. In environmental emergency, to determine the level of the pollutants in the water supply for the manufacturing plant to purify a chemical needed to make a product. Okay, let's focus on the forensic application. Okay, for example, you want to analyze the residual analysis from bullet gun or gunshot residue. If we want to analyze the gunshot residue, which is made of from inorganic analyte, so it should be an ionic compound. So to do that, you can use ion chromatography or ion exchange chromatography. For example, you want to analyze drug from toxicology analysis from biological specimen. So you can use GC or HPLC, or we can call as the gas chromatography or liquid chromatography, to do the analysis. Okay, after this, we will learn into specific about the HPLC and GC. So after that, you can be able to choose which kind of analyte is better to HPLC, which kind of analyte or which kind of forensic sample is more suitable for GC. They are both complemented to each other, even though on the paper GC is much more better compared to HPLC. But again, it's not necessarily that GC is always better compared to HPLC. Some of the analysis cannot be done using the GC, but can be done using the HPLC. Okay. Here is the what we call the chart of the chromatography. Okay, here is the mobile phase. Okay, here is the stationary phase. Okay, basically chromatography was given its name based on its mobile phase. Okay, for example, in GC, gas chromatography, the name comes from its mobile phase, gas. In the HPLC, high performance liquid chromatography, the name also came from its mobile phase, liquid chromatography. I have not have the chance to use supercritical fluid chromatography. I also have not heard any staff in the faculty have used the SFC for the time being. So in this study, we will only cover on the gas chromatography and liquid chromatography, which is the one that is the most commonly or popularly used in the world of analysis, especially for forensic application. In the gas chromatography, the stationary phase can be liquid or solid. It can be further named GLC or GSC, gas liquid chromatography or gas solid chromatography. For the liquid, it can be liquid chromatography or paper chromatography. If the stationary phase is solid, we can have the liquid solid chromatography, or we can have the bonded phase chromatography, or we can have the ion exchange chromatography, or we can have the size exclusion chromatography, where the stationary phase is solid. Okay, so don't worry. Next, when we enter the chapter of the liquid chromatography and the solid chromatography, you can understand it much more better. Okay, the next one we will learn about the terms in the chromatographic world. Okay, if you look over here, T naughts here or T naught here represent the time of an retained compound, or we can call as the dead volume. Okay, again, T naught or T0 we can call as the dead volume, or we can call as the unretained compound. What is unretained compound? The unretained compound is the one is not interacted at all with the stationary phase. Again, the unretained compound is the compound that will not retain at all with the stationary phase. So it will move as the movement of mobile phase. For example, if the mobile phase needs to take a time to elute from the injector until it reach the detector is about 2 minutes. Okay, again. For example, here is your injector and then here is your detector. Okay. So if your solvent, your mobile phase time taken to reach for the detector is about 2 minutes. The analytes that move along together with the mobile phase, with that also in 2 minutes also we call as the unretained compound. It means it just flow with the mobile phase without interaction at all with the stationary phase. TR, or we can put the numbering TR1 or TR2. Okay, TR is the retention time. In this figure, TR1 is the retention time of the compound 1 or component 1. TR2 is for retention time of the component 2. So usually we use word TR for retention time, or the other name that you can put is RT for retention time. Okay. If we look over here, we have the W1 and W2. Okay, or W half. The W1 and W2 represent the distance between the earlier part when the peaks begin until the peaks end. Okay, it can be measured by two ways. Either you use the ruler by measuring the distance in centimeter or millimeter. But in the world of chromatography, the most common one by measuring the time taken from its arising until it's reach the baseline again. For example, it race start from 2.2 minutes and then it reach the peak. For example, it race from 2.2 minutes, and then it reached the peak at 2.5. Where is my pen? Why it's not working? Okay, 2.5 minutes, and then it goes down back to the baseline 2.7 minutes. Okay, so the width of the W1 is 2.7 minus 2.2 minutes. So it's 0.5 minutes. Okay, this is the common measurement used in the most of the calculation. The next one we will look after this. Again, okay, before forgetting, okay, I told about baseline. Baseline is the straight line when there is no reading or response. So here is what we call baseline. Okay. So I hope you guys get the idea. We have the T naught or the dead volume or unretained compound. We have the retention time. We have the width of the peak. Width of the peak can be measured via two ways. Either you can use the ruler to measure in centimeter or millimeter, or more precisely, better if we use the time difference between its rising peak until it reach the baseline. Okay, for here, the example is here 2.7 minus 2.2. So you get 0.5 minutes for the width of the first peak. Same goes, you need to calculate for the second peak width. Okay, next the chromatic. I think we already discussed the TR or RT, the retention time. Time elapsed between injection of sample and emergence of peak maximum. Okay, means during the injection process at 0 until it's emerged. So that is what we call as the retention time. Mobile phase time or dead volume or unretained compound. Unretained compound. Okay, is the time required for an injectant solvent, molecule, or any other unretained compound to traverse the column, also known as the T naught, column dead volume, or column void volume. It means that anything that is not retained, not interacted with the stationary phase. And then we have the adjusted retention time. Adjusted retention time is when the retention time minus the dead volume. Okay, the difference between analyte retention time and column dead volume or column void volume. Okay, I'm not sure how we can call this name T apostrophe R, but it's longer. Better I spell it out as the adjusted retention time. Okay, the next term we will learn about is the capacity factor. Okay. K or capacity factor is a mean of measuring the retention of an analyte on the chromatographic column. So we want to measure the retention of analyte in the chromatographic column. A high K value indicates that the sample is highly retained. For example, you have here maybe the K value is 2, maybe here is 5. When the analytes the retention time become much more longer, for example 5, it means that the retentivity of the analyte is much stronger compared to the one we have the lower K value. Okay, for example, the value of the first peak here is 2 and K is 5. So the second analyte here actually interact much more stronger to the stationary phase. In the world of chromatography, we will try to keep the K value between 1 and 10. If the K value exceed 10, it means that the analyte has spent too much time interacting with the stationary phase. If that happens, we will encounter some of peak broadening. Okay, because okay, let's say is the situation, okay, here is at the few peaks. Okay, the longer it's retained by the analyte, the peak will get much broader. The shorter it's interact with the stationary phase, the peaks become more sharper. So we want to try to keep the retention factor or retention factor value between 1 and 10. It's better to have a high capacity factor, but don't too much. Okay. To calculate the capacity factor, we need to have the adjusted retention time over the dead volume, or the retention time of the peak minus the dead volume divided by the retention time of the dead volume. Again, for measuring the retention factor, we need to have the retention time over the dead volume, or the retention time of the peak minus the retention time of the dead volume or retained compound over or divided by the retention time of the dead volume. That is what we call as the retention factor. The retention factor will never be less than 1. If you get the retention factor less than 1, it means that something is wrong with the calculation or analysis. So the capacity or retention factor is always more than 1. Somebody will say, or somebody will ask, where actually we use the retention factor. Okay. The retention factor is used when we we apply the same analysis at different places. For example, I have the HPLC in Johor and my friend have another similar HPLC in Kedah. So I believe that even though, not I believe, it's usually commonly observed that even though the instrumentation setup is the same, detector is the same, the column is the same, the retention time will be different. But how to make sure they are similar? Okay, to make sure they are very similar, we can calculate the retention factor. If the column is the same, the setup is the same, wherever it is the location of analysis, the capacity or retention factor should be the same. Okay. That's why in terms of my study, my PhD study, there is some question of from the examiner. Okay, the examiner asked me, you perform the you build the database for forensic analysis using GC, ECD and HPLC. But if you do that, somebody else needs to come to your lab and do everything at your lab. How you are going to solve the problem? So we propose the application of capacity factor, since the capacity factor should be the same when the setup of the instrumentation is the same. The retention time will be different, but the capacity factor or retention factor should be similar regardless the location of the instrumentation. How can I explain more easily to you guys? Okay. Okay, for example, in my lab of analysis of the drug, this is the chromatogram. The depth volume is at 1 and the analyte peak or the retention time of the analyte peak is at 5. Meanwhile, for the one for example, at the Firas lab at Iraq, they get the peak like this. So it would be different compared to my chromatogram. Even though the setup is the same, but they get different retention time. So we need to calculate the retention factor to confirm either it is similar or not. For example, in my lab is 5 minus 1 over 1 equal to 4. In Firas lab is 10 minus 2 over 2, which is 4. So the retention time or retention factor or capacity factor in my lab and the one that performed in Firas lab at Iraq is similar. So this is the application of the retention factor. Okay, the next chromatographic terms is the column efficiency, or we can call as the theoretical plate number, TN or N. To calculate or to determine the theoretical plate number N, we need to use this formula. We have two kind of formula. The first one is here and the second one is here. Okay. The first one is 16 in the bracket TR over WB, and then you square the value inside the bracket and then you multiply by 16. For the second value, you have 5.54 multiplied by everything in bracket here, TR over width of half height over square. WB is the width of peak at base peak. WH is the width of peak at half height. For example, here. What is that? Okay, here. Okay. So here is the WB. Okay. For WH, you need to determine the height and then you measure the height, measure the width at half height. So here is WH. So if the question gives you information of the width of half height, please use the formula. Don't use this formula. And vice versa. If the question gives you information about WB, don't use this formula. Use this formula. The higher the N number, the higher the efficiency, the more efficient of separation. A good efficiency corresponds to small peak or bandwidth. If we look over here, the smaller the width, the better it is. Okay. The smaller the width, the better it is. Okay. If you look over here, we have the chromatogram with the smooth line and also with the dotted line. If you look at here with the chromatogram with the dotted line, the peak is broadened. Okay, the peak is broadening. When the peak is broadening, the peak will tend to become broader. Okay, and also the height of the peak is also lower. So it will decrease the sensitivity of the analysis. When your column efficiency has a very good efficiency, the peak will not broaden. The peak becomes sharper. When it becomes sharper, the height of the peak will increase much compared to the one with low efficiency. Then it will help the sensitivity of analysis. Okay. So where is actually importance to have a very good efficiency? Okay. Okay, can you imagine when you want to perform the calibration curve? Okay, you want to perform a calibration curve. Okay. Let's say you have the one with a very good sharp peak and the one that you obtain a very broad peak. Okay. For example, if you look over here, the intensity of the sharp peak maybe here is 10, but the intensity here may be 4. Even though, for example, in this situation, the concentration of both chromatogram, the concentration of the analyte is similar. For example, here is 5 ppm. 5 ppm. Here is 5 ppm. Here is 5 ppm. Okay. So let's say you lower down into 1 ppm. So you can expect that you can still to have the chromatogram. But if in this situation, let's say if you try to inject 1 ppm, maybe you will not be able to have the peak area at all. So that's why we need to have the column or the analysis with high efficiency. So when you doing your calibration curve, you can go to ppb level. ppb level. Instead of here, maybe you can go to ppm level. So you need to have a very good efficiency. Okay, the next one we will learn on the height equivalent or plate height. Okay, it compares the column efficiency of different length of column. Okay, whereas L is the column length and is the theoretical plates. Okay, let's imagine like this. This is your column. You can imagine your column have plate in the inside. The higher the number of your plate, the better the efficiency. Okay. The lower the number of the height is the plate height. Okay, so if we can zoom between here, if we can zoom, we want to, for the HETP, we want to measure the distance between the plate height. Okay, the lower the distance of the plate height, the better it is. Okay, the lower the distance, the better it is. Therefore, the value of the height or HETP or H must be low to get an efficient column. Okay. Therefore, the more efficient the column, the more theoretical plates number in the column, the better the resolution. Again, if we can imagine, okay, for example, you have two kind of column. You have two kind of column. Okay, here the plate height is, they have a similar length. They have the column A here and here have similar length. Okay, here you have the shorter plate height. But here you have longer plate height. Okay, here, if you look here, the amount of plate height is the number of n, the number of the plate number is at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You have 11n. Compared to this column, the same length, you have 1, 2, 3, 4, 5, 6, 7, 8. 8n. So, this column has much efficiency compared to this column. Okay, and also if you look again here, the distance between the column, the distance between the plate height, the distance between the plate is smaller compared to here. Okay, so the column has better efficiency. Therefore, the more efficient the column, the more theoretical plate it is, the smaller the HATP and can provide better resolution. This means that the peaks can get sharper. If you use this column, your peak might be broader. Okay. So to determine the HATP, so you need to measure the distance between the plate height. So you use the column length divided by theoretical plate number. We will look into the example of a question on the plate number and also the plate height. Okay, in the sample problem here, an analyte with a retention time of 407 seconds has a width at the base of 30 seconds on a column 12.2 meter long. Find the number of plates and plate height. Okay, so you need to extract the information. So just draw the chromatogram. Okay, so you can extract the information. So the RT is 407 seconds. And then the problem also mentioned width at the base of 13 seconds. So the width here is 13 seconds. The column length is 12.2 meter. Okay, so we know that for of the n, when we using WB or width base, we need to use this formula, 16 multiplied by RT over WB squared. So 16, the RT is 407 divided by 13 seconds squared. So by using the calculator, 407 divided by 13 squared the value multiplied by 16 is 15682.7 something. So you have the plate number. So you need to calculate the height. Height between plates or plates height is L over N equal to 12.2 meter over this value. So you will get 7.8 times power of minus 4 meter, or you can convert into millimeter, 0.78 millimeter. So let's look at the answer. See, 1.57. Okay, then you get 0.78 millimeter. So again, if you have the problem, you need to extract the information and then you apply at the appropriate formula, to according formula. Okay, the next one we will learn on the resolution or RS. RS is the degree of separation of two components leaving the column. So the RS is the degree of separation between two components. To determine the RS, you need to use this formula. Okay. 2 multiple by retention time differences between peak 2 and peak 1, and also with the addition between the width of peak 1 and also peak 2. Again, as I mentioned in the earlier lectures or in the previous several previous slides, you can use either in centimeter or can use time as the width. Okay, but you need to very constant. For example, if you use the distance in millimeter, so the width you need to use the measurement of millimeter or centimeter. If the differences of D here or TR1 minus TR2, you use the differences of time in seconds, then the width here you also need to calculate in second. Okay, I think I need to correct the, I cannot correct the, because it is a figure. Okay, it's actually TR2 minus TR1. It's not TR1 minus TR2. Okay, you need to correct about it. You need to amend this formula. TR2 minus TR1. Okay, in this situation, where the information given you the measurement in centimeter, so both of the unit you need to use over here is in centimeter. For example, the D over here is 1.8. The width here is 0.8, 0.9. So 2 multiplied by 1.8, you get 3.6. 0.8 plus 0.9 is 1.7. So 3.6 cm over 1.7 cm. So it is 2.1. RS more than 1.5 indicates a baseline separation. What is it mean by baseline separation? It means that totally separated and you get the baseline. Okay. If, for example, you don't have a very good separation, you don't have the baseline separation, the example is like this, where the peak never gets to bottom to the baseline. Same goes to this chromatogram and same goes to this chromatogram. So again, I would like to remind, if the sample problem provide you with the data information of by using the retention time, so better you use to use the retention time. For example, say that here is 3.2, here is 2.8. So 3.2 minus 2.8. Okay. And then to get the width, for example, if you obtain is 2.9 minus 2.7, here is 3.3 minus 3.0, then you need to use that as the width. If the problems or the question doesn't provide you particularly, or you cannot be able to have the information of time or seconds as the data information, then you can use the ruler to apply in this formula to get the RS value. Okay, if we look over here, RS value, if for example here the RS value is 0.5, it means that your peak is totally non-separated. Okay, from here is for example here is 0.75 and here is 1.0. So the minimum is 1.5. The minimum is 1.5. If you are not able to obtain less than if you are not able to obtain more than 1.5, it means that you don't have a very good separation, and sadly, unfortunately, to tell you that your analysis will not be accepted. So let's say, for example, in the next semester, you need to do the forensic analytical instrumentation analysis during the practical. So for the separation between two analytes, you need to be able to achieve at least RS 1.5 if the analysis require separating several analytes. So here is the RS value again, the degree separation of two components. Here is the formula. If the formula is not provided during the examination, you might ask the examiner. Okay, the next one we will learn about the separation factor or selectivity factor. Selectivity and the RS is about the same. Okay, it's also describe the separation between two species. Okay, so it's actually about the same, but in the separation or selectivity factor, you need to use the adjusted retention time. Okay. The adjusted retention time of peak B over or divided by adjusted retention time of peak A. This is the selectivity factor. Okay. So the selectivity factor is always greater than 1. High selectivity factor indicates good separating power and good separation between a pairs of each peak. A pair is what? A pair is the tips of the peak. Okay, but to have a very good understanding, to actually to have a very good separation, you need to calculate for resolution. Okay, for the selectivity factors, it's just for the separation between two peaks of a pairs of its peak. I mean the tips of peak. So it's not, for me, it's not preferable to calculate the selectivity factor. But if the question require you guys to calculate the selectivity factor, you guys need to be able to calculate. In my opinion, it is better to determine RS value instead of alpha value. The next one is the effect of efficiency selectivity on the resolution. Okay, if you look over here, the n is 250. Okay, if we have here, the n is 1100. So if we look over here, the efficiency of the column of here between here is weaker compared to the C. Okay, so that's why we see the N peak, the C chromatogram is much better in the peak shape. The peak is much more sharper. Let's look on the RS. RS is for resolution. RS less than 1.5, it shows that they don't have the separation. If RS, the value is more than 1.5, it means that we can have the total separation. Between these three chromatogram, if we look over here, chromatogram A is 0.8, meanwhile B and C is 1.8. And the RS value at 1.8 is mean that the chromatogram will be able to have a total separation. Okay. If you have a good RS, it means that you have a good selectivity. Okay, I think that's it about the effect of the efficiency selectivity on resolution. Okay, the question can ask you about this. Okay, for example, please explain between all these profile of chromatogram. So you need to be able to discuss. For example, it gives you the chromatogram, gives you the efficiency value, RS value, and alpha value. So you need to discuss accordingly. Okay, so you need to discuss based on your understanding. Okay, for example, like I have discussed before this. Okay, here is the next data interpretation assignment. I will open the submission of assignment in the e-learning. Okay, so you need to answer this and discuss accordingly. So you need to calculate and discuss your finding. Okay, hi everybody. Good night. Okay, if you can see, my t-shirt is all changed because right now I am at home. Couldn't finish the lecture at my office because I do have a meeting this afternoon. Okay, let's go about the peak asymmetry. Okay, peak asymmetry can be divided into two: peak tailing and fronting. Okay, tailing is something like this. The broadening is at the end side. For the peak fronting, the broadening is at the front side. In the ideal world, all chromatographic peaks would be symmetrical. Should be symmetrical in the ideal world. However, due to the effects of instrument dead volume, adsorptive effects of the stationary phase, and the quality of the column packing, peaks may show a tailing behavior. So we have this kind of problem. The depth volume, adsorptive effects, either the mobile phase is not suitable for your sample, or the quality of the column packing is not that great anymore. It can affect the peak asymmetry, so it can cause the fronting or tailing peak. Tailing describes peak whose tail portion is wider than the front portion. Okay, here is the tailing, when the portion of the tail is much more broad compared to the front. Also, if the sample concentration is too high, or if the column is damaged and contains channels in, then a fronting peak shape may occur. Okay. Let's look into the tailing. Okay, here is the example of tailing peak, where the portion of the peak at the end is much wider compared to the front. Okay. If we calculate the area of the on the tailing side is much more larger compared to the front one. This is what we call as the tailing peak. Okay, if we can see over here, okay, we can see that our analytes or our solute is not run at the optimum condition. The optimum condition is mean that they all run at the same pace. Okay, but in this situation, some of the analytes, some of the particle of the analytes, or some of the molecule of the analyte, or some of the atom of analyte is left behind. Okay. In the case of chromatography, we always refer to molecule or compound. So some of the molecular or solids of the analyte were left behind. Okay. So when it's happened, we will have the tailing peak. Okay. So it means that there is something left behind. The tailing peak asymmetrical is due to column void, okay, blocked freight or not suitable mobile phase system. Okay. Here is the example of figures where we have the column void. Okay. Where the column void, where, okay, actually some of the analyte enter too fast. Okay. And some of the analyte will move towards through the column towards its supposedly a natural path. Okay, so we have the column void over here. Okay, when it's happened, most of the analyte will move fast. If you can see here, the void is a bit large. Okay, so most of the analyte will move fast. Some of it will left behind. Okay, because they move through the right path. Okay, so when it's happened, it can cause the tailing peak, or it can be due to the blocked freight. In example here, okay, between the column, if we look at the HPLC column, okay, HPLC column, they have guard and also the column. Okay, between guard and the column, they have freight. Okay, freight act as the filter. Freight act as a filter. So when the freight is blocked, so some of the analyte will left behind. So it will cause the tailing peak. Okay. Usually, if we have the problem of the tailing peak, we will try to change the freight first. Okay, we will try to change the freight first, or we will try to change the freight. Okay, we will open the column, change the freight with a new one. But if we already change the freight and the peak is still tailing, that is mean it can be a column void. If the column void happens, usually we just buy a new column. Okay. Or in the other situation, when you are using the mobile phase by using a mobile phase with adjusting pH, for example, you need to use the analysis that required mobile phase with a high pH, it can also cause this kind of behavior. So if not suitable, if the mobile phase is not suitable to the sample or to the column packing material, it can cause this effect as well. Okay, to do that, to avoid that, okay, to avoid not suitable mobile phase, what you can do that you can dissolve your sample that using the mobile phase solver system. For example, your mobile phase solver system composed of acetonitrile water at the pH of 3. So you can use the mobile phase system, acetonitrile water 7030 at the pH 3. You can use that system to dissolve or to prepare your standard. Okay, so this is the kind of the idea. Okay, the next one is the peak fronting. Peak fronting describes a peak whose front portion is wider than the tail portion. The front portion is wider than the tail portion, or you can call it the front portion of peak area is much larger compared to the tail portion. As long you can understand how the peak shape, if the question has been asked, it can be accepted. Okay, most of it due to sample overload or wrong sample solvent. Okay, to overcome due to sample overload, what you can do, you can reduce the concentration, or you can reduce the volume of injection. Okay, so what you can do, reduce the sample injection, or reduce the concentration of sample. Okay, it means that your analyte is too concentrated, so it cannot move at the optimum peak. Okay, if in my practice, if I have the fronting peak, the first thing I do is try to reduce the concentration. Okay, or I reduce the sample injection. Okay, in HPLC, we use normally about 20 microliter. So the first thing first, I will try to reduce to 10 microliter. Okay, after that, if the peak fronting still happen, then I will dilute my sample. Okay, because this is the easier one. Reducing the sample injection volume is the easiest one. And then I will try to dilute my sample. Okay, if still cannot, then I need to perform the suggestion as the previous one, when I need to prepare my standards using the mobile phase system. Okay, I need to use the solvent system to dissolve or dilute my sample, or preparing the standard using the mobile phase system. So then I can achieve again my fronting peaks. Okay, if you have heard about the split peak or the broadening peak, okay, I'm not including in this slide. Okay, just want to tell you based on my experience. Okay, if you have encountered a split peak that you believe it comes from the same sample, okay, or the bouldering peak, it's usually due to wrong sample solvent. It's not about the sample overload, or what we call is the column void. If this happen, if the split peak or the boulder peak, it will not be caused by sample overload, but it can be happen by wrong sample solvent or dead volume. Okay, dead volume or block curve freak will cause the split peak or bouldering peak. Okay, or wrong sample solvent. If I encounter with this problem, what I do is I use the system, mobile phase system, that is to dissolve or prepare my standard or my sample so that I can improve my chromatogram. But if I already adjusting my wrong sample if I already use mobile phase to prepare my sample as standard and I still get the splitting and bouldering, then the next thing I try to change the freight. Okay, if the freight has changed but still have the problem, it means I have a damaged column due to column void. Normally, if we have the problem with the column void, we just change to a new column. Okay, usually in the past years, I included how to calculate the peak asymmetrical in this study, but I believe uh, it doesn't necessarily for you guys to learn that, so I skip that part. I won't ask in the final examination question. Okay, but it is a very good knowledge for you guys to learn. Okay, other than peak asymmetrical, another problem that always be encountered during a chromatography analysis is band broadening. It means that the band is too broad. Okay. It is well recognized that column band broadening originates from three main sources: multiple pass of an analyte through the column packing, or molecular diffusion, or effect of mass transfer. So, okay, before we go in further, if you look back at the peak asymmetry and peak broadening, the kind of the question can be asked to you guys encountered during examination is describe peak asymmetrical. Okay, how to avoid or how to improve. Okay, that is the kind of question. For example, the question, please explain about three main sources of peak broadening. So you guys need to be able to understand the concept of peak broadening or differentiate between peak band broadening or peak asymmetrical, or how you can improve the band broadening and peak asymmetrical. That is the kind of, I think, a very popular question to be asked in the examination. But you need to understand instead of memorize. So again, there are three main sources of band broadening or peak broadening. The first one is multiple pass. The second one is molecular diffusion. And the third one is mass transfer. In the next slides, we will discuss into detail about these three kind of effect or sources to band broadening or peak broadening. Okay, now let's look to the Van Dimter equation and graphical representation. Okay, if we look at this graph alone, it is HETP versus linear velocity. HETP is the height plate of the column plate number. Linear velocity shows the flow rate of the mobile phase. Okay, as we know, the lower the HETP, the better it is. Again, the lower the HETP, the better it is. Okay. Here we have the A, B, and C. A is for eddy diffusion or multiple pass effect. B is random molecular diffusion. And C, mass transfer within particle caused by a mobile phase. If we look at the A, eddy diffusion or multiple pass effect. Okay, if we look over here, if the peak broadening caused by the eddy diffusion, regardless of any increasing of the velocity or the flow rate of the mobile phase, it will not change the peak broadening. It will not improve or decreasing the effect of peak broadening. Okay. In the B, okay, the B is the random molecular diffusion. Okay. If you want to counter the random molecular diffusion problem, you need to use high velocity of flow rate. If you can see, at high velocity of flow rate, the random molecular diffusion is less. Okay. If you look over here, as the velocity increasing, the HETP or the plate height become more lower, so become the efficiency of separation become more better. On C mass transfer within particle. To counter the problem of mass transfer band broadening, you need to use low velocity. You need to use the flow rate at low velocity. So if we look over here, the cross section between all three mass transfer or all three sources of band broadening, is at this point where you just need to find a good velocity that can counter that, not too fast or not too low. If you become too fast, if you use the flow rate too fast, you will increase the effect of the mass transfer. If you use the velocity is too low, it will decrease the efficiency, or it will increase the effect through the random molecular diffusion. Okay. Let's look into the first source of band broadening. The first one is eddy diffusion. Eddy diffusion is a process that leads to peak broadening due to the presence of multiple flow paths through a packed column. It means that the molecule have different paths to reach the detector. Okay. For example, we have the molecule 1, we have the analytes that have some of its molecule into 1, into 2, and into 3. For example, our analytes is consists of 3 molecule. For example, for X analyte, it has the molecule of X1, X2, and X3. But because of the multiple path over here, okay, it can cause peak broadening. Okay, the one that move with the shorter path will arrive first. Okay, the second one is through a moderate path. The last molecule that reach and or pass through a longer path will cause the peak broadening effect. Okay. A solid molecule travels through column, some arrive at the end sooner, and then the others simply due to different paths travel around the support particle in the column that results in different travel distances. Okay. So because of different travel distances, it can cause the peak broadening effect. Okay. This is happening because the column material is not well packed. Okay. To reduce the effect, okay, we need to reduce the stationary phase particle size. As the stationary phase particle size become more smaller, so we can prevent the pore inside of the column, or we can reduce the volume inside of the column, can provide the extra distance or multiple path to the molecule of interest. Okay. Again, in the eddy diffusion, if we look over here, okay, if you increase the velocity, it will not help in increasing the efficiency. So it will not affect by increasing the velocity. To counter the eddy diffusion or multiple path, you can use well-packed column, use a smaller stationary phase particle, or using a particle with a narrow size distribution. It means that you need to, the column must be well-packed. Okay, I think you guys already understand about it. And then you can reduce the particle of stationary phase. For example, instead of 4.5 micrometer per particle, you can use 2.5 micron. Okay. The next solution is using particles with narrow size distribution. For example, instead of you use the column diameter at 10 mm, okay, you can use the diameter with 5 mm. Okay. This will reduce the effect of, or it can reduce or minimize the eddy diffusion effect. Okay. I think that's it for eddy diffusion. Do I have the things I forget? No. So in summary, eddy diffusion is due to multiple paths, okay, with some of the paths has different distance or has the longer distance. Because of the longer distance, some of the analyte molecule will reach the detector late, so it will cause the band broadening. So you need to understand the concept. Don't memorize by words. As long you'll be able to describe the concept based on your understanding, you can get the marks accordingly. For example, if the question asks you, please describe one of the effect band broadening. So you need to discuss accordingly. For example, if the question consists of 3 marks, so you need to have 3 points. If the question have 5 marks, so you need to provide 5 points. So you need to discuss the problem, okay, describe in detail how to improve. Okay, that is kind of the answers that I believe will be expected to be answered, to be given by the student to get a full mark. Okay, sometimes in the past years, I believe it's not during my time yet, during the previous lectures, they give this draft, and suddenly they need you guys to be able to describe about this. So please be not be prepared to memorize, but understand. I believe in my question, lot of question, especially in the PLO2 or PLO3, I will always ask the question based on understanding, not on the memorization. Okay, next, let's look to another source of band broadening, which is longitudinal diffusion. Band broadening due to diffusion of solutes along the length of the column in the flowing mobile phase. Okay. Results from tendency of solute diffuse from concentrated center of a band to more dilute regions or on either sides. Okay. In the longitudinal diffusion is that the diffusion of the solute along the length of the column. As your analyte pass through the column, it will tend to dilute from the center of the concentrated area to more dilute area. For example, at the early injection is at the center, as is move along the column, the center will diluted to the diluted side. or dilute regions. Okay. This happen occur primarily in the mobile phase, not in the column. Longitudinal diffusion inversely proportional to mobile phase velocity. Okay, we look after that. Higher velocity provide less time for diffusion to occur, means no band broadening. Okay, if you look at the graph, okay, if we use high velocity or flow rate of the mobile phase, we can increase the efficiency of separation. If you look here, the HETP number become less at the high velocity. That's why high velocity provide less time for the higher velocity will be able to avoid or to minimize the longitudinal diffusion effect. How? Because we provide less time for diffusion to occur. Okay, so as suggested here, using a higher mobile phase flow rates, keep system tubing short and as narrow as possible. Okay, so you need to use a narrow tubing. Tubing is the tube that required to transfer the mobile phase until it reach the column and also detector. You need to use the tubing that short as possible. Okay. Use correct nuts, ferrules and fitting wherever possible. Okay. I believe if you can remember two of it, you can also at least you need to remember two of the solutions. If we look again at the chromatograph, if we look at the graph, not the chromatograph, if we look at the graph here, you can understand. Or if we can imagine the longitudinal diffusion effect, we can solve the problem. We know that as the flow rate is slower, it will cause the longitudinal diffusion become worse. So we need to increase the speed. How we can increase the speed again instead of increase the velocity? We can improve the speed until it reach the detector by keeping the tubing system short. Okay, that is how actually you need to understand how you can improve the speed of the analyte to reach the detector. The first one, you can increase the velocity, and the next one, you can use a shorter tubing system or as narrow as possible. Okay, that's it about longitudinal diffusion. We already learned about the multiple path, okay, or we call as the eddy diffusion. Okay, the next one we will learn about the mass transfer. Okay, the last source of band broadening is mass transfer. What is mass transfer? Mass transfer occur when the solute move between the mobile phase and the stationary phase. We call this movement between phases is mass transfer. It means that the analyte will move from the stationary phase to mobile phase, and the analyte in the mobile phase will move from the mobile phase to stationary phase. So they will keep exchanging to achieve the equilibrium. So we call this as the mass transfer. So we can imagine that solutes in the mobile phase will try to move the stationary phase, and solute from the stationary phase will move to the mobile phase. In this figure, we have 4 A, B, C, and D. Okay. If we look in the mass transfer, okay, for example here, if the mobile phase is faster, so it can create the differences in equilibrium. When it's happened, the solute from the stationary phase will try to go to the mobile phase, and the solid from the mobile phase will go to the stationary phase. Okay. When it's happen, okay, when it's achieved its equilibrium, it will cause the peak broadening. Again, in the ideal situation, the movement between the movement of the analyte or solute between the mobile phase and the stationary phase, they will move at the same phase. Okay, when do you have the when do you have the mass transfer effect? Okay, when you apply at high velocity, okay, of the mobile phase, it can create the differences of equilibrium. So, if we look over here, they try to achieve the equilibrium again. Okay, so analytes from the stationary phase will try to move to the mobile phase, and from the mobile phase will move to the stationary phase. When it's achieved back its equilibrium, the peak of the analyte become okay. So what cause of the source of mass transfer? Mass transfer occur when the stationary phase has large porosity or high in porosity. If we look at the figure here, the stationary phase has a lot of pores, or the porosity is so high. When the porosity is so high, the mobile phase that inside of the pore becomes stagnant. It will not be able to move. That the analytes inside of the stagnant mobile phase will not be able to move as fast as possible with the mobile phase. Again, the mass transfer effect is caused by the high porosity of the stationary phase. When the stationary phase has a high porosity, the mobile phase inside the pores becomes stagnant. When the mobile phase in the pores becomes stagnant, it will not be able to bring the analytes out from the pores and move with the flow of the mobile phase, or move with the mobile phase. So when that's happened, the analytes will diffuse or penetrate deep inside the pores, and they will be only able to reach the mobile phase, or the flow of the mobile phase, via diffusion. Okay, when that's happened, it will cause the differences in the time of the elution, okay, and will cause the analytes band broadening. These effects may be minimized by reducing the size diameter of packing material. So, for example, we already learned they have different kind of packing material, for example, 4.5 or 2.5 micrometer. So, you need to go as low as possible. Okay, as low as possible. And you can also reduce or minimize the problem by using low velocity of the flow rate, low velocity of the mobile phase. If you look at the graph here, if you use at high velocity, the effect of the mass transfer become much more apparent. Okay, if you look here at the HETP number become higher as the velocity increasing. So we need to use at low velocity, but we need to keep in mind, if we use low velocity of the flow rate, it will cause the effect of random molecular diffusion become much more higher. So we need to find the optimum flow rate. So how we can minimize the mass transfer effect? Using smaller diameter of stationary phase particles. Use the lower mobile phase flow rates. Or we can heating the column. At high temperature, the diffusion process are speeded up. and differences in elution time from particle pore are reduced. So these are three solutions to minimize the mass transfer effect. So separate in the next slide, the pressure of mixtures depend on the width of the solid peaks. Okay, we want the narrow peaks for better efficiency, and the spacing between peaks or the baseline must be larger for better resolution and selectivity. Again, for high efficiency is where we get a narrow peaks. High resolution and selectivity when we are able to separate or get the baseline between peaks. So here we want to get a sharper peak. Okay. In the spacing between peaks, we want the spacing or we want the baseline is large. The separation between two peaks or two analytes, we want it well separated. For the column efficiency, more N give narrower peaks and better RS. In the capacity factor, if low capacity factor analytes will not be retained enough for good separation. So analytes need to have ideal capacity factor. For the selectivity, if analytes have a very similar selectivity, then they will be very difficult to separate. So you need to calculate the selectivity. The selectivity number must be difference between analytes. So to improve the resolution in chromatographic separation is the first one based on the column construction. Okay. The resolution is we want to improve the separation between two analytes. Okay. To improve the separation between two analytes or resolution, we need to increase the column length. Okay. And we can also try different kind of stationary phase depends on the analyte's characteristic. For example, if analyte is polar, it's better for us to use the polar stationary phase to provide a better separation. If we are using gas chromatography, we can decrease the column internal diameter to allow for a better separation. In the liquid chromatography, we can try to use different mobile phase system that is actually compatible with our analyte of interest. Okay. And then in the column construction, we can use smaller and more uniform particles. Okay. Based on the column operation, okay, we can optimize the flow rate. Okay. So we need to find a good flow rate, not too slow, not too fast. We can also reduce the sample size in terms of volume of injection or concentration of injection. Volume or concentration. For GC, if we want a better separation, we need to not decrease the column temperature. It means that I need to amend it. Programming. Not flow, RAM programming. Okay. Okay. If we are using GC, we can improve the separation if we are using low column temperature RAM programming. For example, your analytes The first one is the boiling point at 65 degrees Celsius. And then the second analyte at 70 degrees Celsius. And then in this chromatogram, you use the temperature programming is at 5 degrees C per minute of increment. It means that every minute it will increase 5 degrees per minute for the oven programming. If you want to improve the separation, maybe like this, you need to reduce the temperature RAM of oven programming. You need to reduce, for example, 2 C per minute to achieve a better separation. Okay. So here is the general factors in increasing the resolution. Increase the column length, decrease the column diameter. You can also decrease the flow rate. Use the column with a very good packed material. Use uniform stationary phase. Okay. You can decrease the sample size. Select a proper stationary phase. Select a proper mobile phase. Use proper pressure. Use gradient elution. Okay. This is the general factor to increase the separation between analytes. So I believe in the question is never be more than 5 marks in my question of examination. Usually I don't put a question more than 5 marks, at most 6 marks. So don't remember everything, but I believe if you can understand the concept or the problem and how to solve it, I believe you can remember all of this, or you can understand to describe all of this. I believe the number 10 and number 9 and number 10 I have not described very well, but I believe when we learn in the HPLC especially, we are be able to understand how to use the proper pressure and also gradient elution to provide a better resolution. Again, if you don't understand anything, you can always ask in the group WhatsApp so we can share the information with everybody else. I believe I myself is not perfect, so we will try to learn the one that we cannot understand together. Okay, the next one we will discuss on how you should or how you can present or discuss your result. How you can present or discuss your result. Okay. If you are doing analytical analysis, instrumentation analysis that require instrumentation, so you need to be able to discuss the result based on qualitative analysis and also quantitative analysis. In the qualitative analysis, you need to discuss the retention time, peak resolution, peak selectivity, and the peak asymmetry. Okay, I believe you guys all already know. Okay, the retention time, the peak resolution, between this, and also the peak selectivity for the alpha, or if you have the front peak, the tailing peak, or you have the fronting peak, you need to describe. In the quantitatively, you can also discuss on the reproducibility or repeatability. In reproducibility and repeatability, we try to discuss either our analysis is repeatable or not. It means that you run today, you get the same retention time. Tomorrow you run, you also have the same retention time. Or today you run 1 ppm, you get 1 ppm. Tomorrow you run, you also get 1 ppm. Not suddenly you get 3 ppm. For the accuracy and precision, for example, you have the calibration curve and you run the standard you get 1 ppm. For example, the standard you know that is 1 ppm, and then you run, you must get 1 ppm as well. On the quantitative analysis also, you need to provide the calibration curve. And then from the calibration curve, you can determine limit of quantification, limit of detection, and percentage recovery. What is calibration curve? Calibration curve is like this, where you run the analytes at several points. For example, 1 ppm, 2 ppm, 3 ppm, 4 ppm, and 5 ppm. Okay. This calibration curve is really important for quantitative analysis. Without this, you cannot determine how much the amount or the concentration of your analyte of interest. For example, here is the concentration, here is the what we call is the area. Okay. So let's say you have the sample A. The sample A give you area 1000. Okay. So you can use this calibration curve to determine the concentration. For example, here is 3.5 ppm. Okay. So this is why calibration curve is really important. Okay. What is limit of quantification? Limit of quantification is the minimum amount that you can quantitate. In the calibration curve, the LOQ value must be in between of the calibration curve. If your LOQ is either lower than the point of the calibration curve or more than the point of the calibration curve will not be accepted. So limit of quantification must be in the calibration curve. Maybe in this example, the limit of quantification is 1.5 ppm. What is the limit of detection? Limit of detection is the lowest amount of the analytes can be detected. But it's not, we can only say that, for example, okay, before we going further, for example, the LOD you determine as 0.2, but your calibration curve you make from 1 to 5 ppm only. Let's say, for example, from the calibration curve, okay, you are not be able to do the process. For example, yeah, of course, because you do from 1 ppm, you cannot use the curve to determine the concentration. Maybe I need to draw a little bit larger. Better I just discard. Okay. Okay, let's say here is the calibration curve. Maybe here is your LOD. LOQ. And here is your LOD. 0.2 ppm. Okay. Let's say, for example, you have the area within this one. So you will not be able to use the calibration curve directly to calculate the sample because you don't have this line as the references. So you cannot know exactly. Okay. But you have the virtual line you can use. When this happens, we cannot say accurately that it has been quantified. But we can say that it was detected at this concentration, for example, 0.5 ppm. But we cannot exactly say that it was quantified at 0.5 ppm. Okay. We need to mention that it is be able to detect at 0.5 ppm. Okay, but lower than the limit of quantification. Okay. And then the next thing is the percentage recovery. Percentage recovery is the thing that you must provide in the instrumentation analysis. What is percentage recovery? Percentage recovery is for the extraction process. For example, you have the analyte that you spike in the sample 1 ppm, and then you try to extract. After the extraction, you run through the instrument. From the instrument and the calibration curve, you get 0.97 ppm. So you can say that 0.97 ppm over 1 multiplied by 100. So you get about 97% of recovery. So percentage recovery is the one that you extract from the sample, or you extract from the simulated sample to test if your method of extraction is good enough or not. You want to test the extraction method is good enough or not. For percentage recovery to be accepted, it need to achieve between 80 to 120%. Accuracy and precision also between 80 to 120%. Okay. For the reproducibility and repeatability, the CV you need to obtain less than 20%. Okay. But if you deal with the drugs, pharmaceutical, or biological sample, you need to obtain less than 10% for CV and 90 to 110% before your data can be accepted. I won't discuss into detail, but it's the kind of information that you need to learn for you can have a very good discussion during the practical analysis or during your dissertation. But I believe this kind of information will not be asked too much in the examination. So it's just for your information. But I believe it will benefit you guys during the forensic practical and also dissertation. Okay, hi everybody, good morning. Okay, now we will continue on the part of calibration methods, which are already been described in this slide. Okay. The calibration methods is the kind we need to do to perform any quantitative analysis. Without calibration methods, our quantitative analysis will not be able to perform or will not be accurate. So the calibration method is very important in every instrumentation analysis. That's why in this study, we will learn into detail how to perform the calibration methods. Okay, the first type of the calibration method is external calibration. External calibration is the most common calibration method, has been used widely in the analytical laboratory. External calibration method is a term used for a normal calibration curve of range of standards which solvent is used to is different from sample matrix. It means when we do the calibration curve, okay, when we prepare our analyte, we use solvent. Okay, so we don't use sample matrix to prepare our analytes. For example, for analysis of copper in river water, to perform the calibration curve by using the external calibration, we actually use solvent to prepare the calibration method. In some kind of the other calibration methods, they will use the river water itself as the solvent for sample matrix. But in the external calibration, the solvent used is different from sample matrix. Normally, we will use the solvent that can be produced in the lab or can be buy from the other company, such as acetonitrile, okay, such as methanol, or we can just use the ultra pure or distilled water that can be obtained from the laboratory. The grade of the solvent depends. The grade of the solvent depends on what kind of the instrumentation. For example, if we would like to use HPLC or high performance liquid chromatography, we need to use HPLC grade at least to perform the to prepare the external calibration. If, for example, we would like to use gas chromatography, so the solvent that we need to use must be GC or gas chromatography grade. If the analysis only require water as the solvent, we can use distilled water. But the most preference one of if water need to be used as the solvent, we need to use the ultra pure water. Most analysts prefer to use calibration standards to generate a linear curve. Okay, this curve shows the relationship between signal and analyte concentration. So if we look at here, the one that I draw, okay, is the plot between the signal and the concentration. So by right, as the concentration of the instrument, as the concentration of the standard increasing, so with the signal of detector or detection. Okay. However, there are cases when external standard calibration curve cannot be accurately and precisely measure the concentration of analyte. For example, when we face the complex matrix. Okay. Complex matrices are common example when external standard methods may fail. Complex matrices like soil or plasma contains many substances that cannot be entirely removed during the sample preparation process, and they may interfere with the analyte analysis in several ways. To compensate this, standard addition or internal standard must be used. Okay, so in some ways where we do the external calibration when we don't have the complex matrix, we can use the external calibration when the matrix is not that complex. It means that the matrix such as tap water or river water that not so cloudy or not so what we call uh, not so contaminated, for example. Okay, we got water. But if we use the complex sample such as soil or biological sample, the external standard methods may fail. May fail is mean that the calibration curve we use, we cannot determine the amount or the concentration or quantitative analysis accurately. Okay, so when our external calibration is not be able to accurately determine quantitatively, so we need to proceed with other kind of calibration methods that are more suitable for the complex sample. Okay. Another factor that can affect the usage of internal standard is the fluctuation of instrumentation reading. To compensate this, internal standard is compulsory. Okay. Other than complex matrices, so other factor is the fluctuation of instrumentation reading. If the fluctuation of instrumentation reading is occur or appear, so we need to use internal standard calibration methods. Okay, but I just want to say here, it's not necessarily when you have the complex matrix, you cannot use the external calibration method. You can use external calibration methods if you have a very good extraction method. If your extraction method will be able to remove the interference as much as possible, and then it means that you are able to use the external calibration methods. Okay, so how to determine either we can use the external calibration or not? Let me have some drawing. Before we going further into the before we going further into the standard edition and internal standard edition to compensate our issues before this, let's just take a look on the external standard calibration ideal graph. Okay, here is the external calibration graph. Okay, where we make a graph signal versus concentration of analytes. Okay, for any kind of analysis, you need to use at least 5 points. But in the normal practice, you need to use 6 points of calibration methods. For example, 1, 2, 3, 4, 5, and 6 ppm. Okay. From the calibration method, for example, you run the sample unknown, you will have the signal. From the signal, you can tailor with the graph to obtain your sample concentration. For example, in this situation, it's about 4.5. Okay. For example, okay, the 1 give 100 signal, 2 give 200, 3 give 300, 4 give 400 signal, 5 give 500 signal, 6 give 600 intensity of signal. So when you have the sample unknown, it shows the signal as 450. When you use the graph, you draw along the line and goes back to the concentration baseline here. So it will show you the exact concentration of the sample unknown. Okay, that is how you can perform the external calibration method. Okay, this is just a very necessary thing to tell you. Okay, through the calibration method, we can get the y equal to mx plus c. Y equal to mx plus c is the equation we usually get. Y is the signal. M is the slope. X is the concentration. C is the y-intercept. Okay. Again, Y is the signal. M is the slope. X is the concentration. C is the y-intercept. Usually, they will give the equation like this. Y equal to 2x plus 2, for example. Okay. So, if you get the signal of the unknown, you just need to put inside the y. For example, 450 equal to 2x plus 2. So, then you need to use the calculation to find x. For example, this situation is x equal to 448 or 450 minus 2 over 2. You will get what is the concentration of x. That is kind of example. Okay. The other thing that you need to pay attention is when you're doing the calibration curve, you will also get the R-squared value. The R-squared value you need to obtain at 0.995. Okay. The R-squared value you need to get is 0.995. If you get less than 0.995, you need to repeat the process until you get 0.995 and above. Anything below than 0.995 it cannot be accepted for chemistry for instrumentation analysis. So the R-squared value must be 0.995. Okay. By doing the calibration curve as well, you can determine the LOD and LOQ. Okay. The LOD usually must be lower than the range of the calibration curve. For example, from 1 to 6 ppm. For example, here you make the calibration curve from 1, 2, 3, 4, 5, 6 ppm. When you did the LOD, when you do the LOD determination, the LOD value must be below than this range. For example, the LOD value must get below than 1 ppm. You get maybe 0.2 ppm. That is okay. But for example, if your LOD is more or inside if the calibration curve, for example, you get 2.3 ppm, that is mean there is something wrong with your calibration curve or calculation of LOD. LOD can be determined via two ways. Either you can use the manual injection system. Okay. Better if I draw again. Okay. So again, when you're doing the calibration curve, okay, you will get the y equal to mx plus c, and you will also get the r squared value. Okay. Then you will be able to determine the LOD. As I mentioned before, the LOD must be lower than the calibration curve range. Okay. The LOD can be obtained via two ways. Either you can use the formula inside the Excel, or you can use by doing the injection manually. How to determine by formula? Okay, I will leave it for you guys to learn by yourself. But if you don't understand, you can always come and see me, or you can always text me, or to make sure that you'll be able to perform the LOD. Okay, so we can determine it using Excel calculation. The other one is by using manual or naked eyes. Okay, how determine manually? Okay, have you heard about signal to noise ratio? Okay, have you heard about the signal to noise ratio? So when we do the chromatogram, we have the signal, and so we have the noise. Okay. For manual determination of LOD, we need to inject the lowest possible of analytes until the height ratio between the analyte to peak or to noise is about 3 to 1. Until you achieve the 3 to 1, then you can say that you have reached the limit of detection of your analyte. Okay. But I believe this kind of LOD is very hard to do, so it is much more preferable if we can just do using Excel calculation. If I'm not mistaken, it's about 3.3 slope over, I think, yeah, it's okay. Okay, let I show you the thesis from my student. So let's look at her chapter 3. Yeah. This is the formula. Okay. 3 multiple by standard deviation over the slope. Okay, the standard deviation you can obtain by calculating through Excel. For LQ is 10 multiple SD over slope. This is the formula. Let's look at her calibration curve. This is her calibration curve. The point she used is 5 point. The R square is 0.998. Okay. The R square value is 0.998, which is more than 0.995. So the calibration curve is accepted. Then here is the y equal to mx plus c. Usually when you're doing the calibration curve, you will get this formula. This formula you can use to determine the unknown. When you get the, for example, the peak area ratio, or you obtain the signal, you can insert as the y value, and you can determine x, and x is the concentration of your sample. Other than that, okay, we already mentioned about y equal to mx plus c. We already mentioned about the R squared value. We already mentioned about the LOD. And the last one is LOQ. Okay, in the LOD, you can determine using the formula or manual. Manual is 3 to 1 ratio. LOD is 3 SD over slope. Okay. For the LOQ, we can also using manual or formula. In the LOQ is 10 SD over slope. Okay. For the manual is 10 to 1 ratio. So the limit of quantification when you obtain the signal to ratio the height, for example, the height of the signal is 10, the height of the noise is 1. So this is when actually what we call as the limit of quantification. For example, in this condition 10 to 1, it gives the signal, for example, at the area of the things is 300. So you need to put into the equation, or you can use this graph to find the concentration for the LOQ. Okay, that is how you can utilize your calibration curve. Okay, the next calibration method is the standard addition. This calibration method is generally used when the unknowns have complex matrices, or in the other way, we are not be able to perform a very good extraction method where we cannot remove the interference. So that is when we need the standard addition calibration methods. In the standard calibration methods, the fixed amount of sample matrix is used to avoid inconsistency of metric effects. Okay, I will describe using this figure after this. And then the response of the unknown is measured normally without the addition of the standard. A known quantity of the analyte is then added to the unknown sample. Different amount of analyte are added to the unknown, so several points reading can be obtained. Then the floods are then diluted to the mark with the appropriate solvent. Check it well and ready for instrumentation analysis. Okay, here is the figure that usually we need in standard addition method. The first one, we need the solvent. We need the stock solution. The stock solution is mean your standard. The solvent is the one that you need to dilute your sample. And then here is your sample, or we call as the unknown solution. Okay, so here is the first flask. Okay, here is the first flask. So you need to add your sample. Okay, here is your sample. Okay, okay. The sample added, or the unknown solution added must be in the same amount to avoid inconsistency of metric effects. So we need to add the unknown solution at a same amount. We need to avoid the inconsistency of metric effects, because we claim that our analysis have the problem of the metric effects. So we need to use the unknown solution as the sample metric as well, but we need to use at the same amount to avoid the inconsistency. Then the response of the unknown is measured normally without the addition of the standard. Okay, this refer to the first one. Okay, the first one. So we just put our sample and add the solvent to the mark. For example, we prepare in 10 ml flask. So we, for example, let's just say in this situation, we just add 2 ml of unknown solution. Okay, we add 2 ml of unknown solution. Okay. So in the first flask, you need to add how much? 8 ml to prepare in 10 ml solution. Okay. So then a known quantity of the analyte is then added to the unknown sample. Different amount of analyte are added to the unknown, so several points reading can be obtained. So we need to add to several flasks, okay, to make the calibration point. Okay, so we need to add known quantity of the analyte. For example, let's say the stock solution is 10 ppm. Okay, we want to add 1 ppm. Okay, and here we add 2 ppm. Here we add 3 ppm. Okay, how much we need to take from the stock solution? How much? So we need to use M1 V1 equal to M2 V2, which is, for example, okay, the flux is what, 10 mil. The final concentration is 1 ppm. Okay, we have the initial concentration is 10 ppm, right? Okay, so what is the V2? V1, sorry. So the V1 equal to 1 mil. So here you need to add 1 mil, and here you add 2 mil, and here you need to add 3 mil, okay, in order to get 3 ppm. Again, for the preparation of the calibration points, here in these three flasks, for example, let's say we have the stock solution of 10 ppm. The first one you want to add 1 ppm. So by using this formula M1V1 and M2V2 for the dilution formula, by calculating here you find the volume. So for the addition of 1 ppm for the 10 mil flask, you need to add 1 mil from 10 ppm. So you add 1 mil. In here, you want to prepare 2 ppm calibration point. So if you put here 2 multiple by 10 is 20, 20 divided by 10 is 2 mil. So here you add 2 mil from 10 ppm to make this calibration flux, or to make this calibration point or this flux to have 2 ppm of your standard. Same goes to the third flux, okay, or the third calibration point, when you want to prepare 3 ppm of the standard. You want to make this flux contain 3 ppm of your standard. So 3 ppm multiplied by 30 divided by 10, you get the V value of 3 mil. So you need to add 3 mil. So in total we have already what? Here we have, okay, here is how much? 1 plus 2. Here is 2 plus 3. And here is 1 plus 2. 2 plus 2, sorry. Because the unknowns should be the same. Here is 3 plus 2. Okay, 2 is for your unknown solution or your sample. 1 is for stock solution. 2 is for stock solution. 3 is for stock solution, or 3 mil. 1, 2, 3 mil of stock solution. 2, 2, 2 mil from the unknown. So after you have add the known quantity of analyte and different amount of the analyte are added, so several points reading can be obtained, then the flasks are then diluted to the mark. So you just need to add the solvent to the mark. In this example, in the first calibrator, you already have 2 plus 1, so you need to add 7 mil of the solvent. Here 2 plus 2, so you need to add 6 mil of solvent. And this 2 plus 3, we already have 5 mil of inside there, so you need to dilute with another 5 mil of solvent to complete to 10 mil flask. Then you need to shake it well and ready for instrumentation analysis. Okay. Again, the standard addition is used when we encounter complex matrix that we are not able to remove the interference. Fixed amount of sample matrix is used to avoid inconsistency of matrix effect. So we add the unknown solution or the sample at the fixed volume to avoid inconsistency of the matrix effects. The response of the unknown is measured normally without the addition of the standard. We just only dilute with the solvent. A known quantity of the analyte is then added. Okay, so we have a few other kind of flasks, few calibration point or few flasks to perform the calibration points. So we add different amount of analyte. For example, we add 1, 2, 3 ppm over here, and then the flux are diluted to the mark with the appropriate solvent. Okay, for example, perform the water analysis, so we add the solvent of maybe DDW, okay, double distilled water or ultra pure water as the solvent. Or if we deal with the organic solvent, so we need to use, for example, methanol or acetonitrile, for example. So we add until the mark, okay. Then we shake it well and ready for instrumentation analysis. So this is the description of the standard addition, how you can perform the standard addition when you need the standard addition. Okay, actually there is other method actually where we want to avoid the addition of the solvent. Okay, the situation where that we want to avoid the addition of solvent when we deal with the trace amount of analyte. When we do that, we just need to use the unknown solution, okay, and then we add the stock solution. But the stock solution amount must be very low. Okay, that is the other kind of the method. I don't want to teach you in detail. You just need to be able to understand this. But if, example, we encounter the trace analysis that you believe that your sample has minimum amount of analyte, so you need to avoid the use of the solvent. So you must avoid to use the solvent because you don't want to dilute your sample. So when that happen, you just use unknown solution and then you add the stock solution. But the stock solution amount that you need to add is very minimum to avoid the inconsistency of metric effects. Okay. So I believe I won't discuss into detail on the second method, but I just need you guys to get the idea. If let's say in the example in the future, you have a lot of metric effects, but also at the same time you don't want to dilute your sample. Okay. Okay. So here is the common way lah. Here is the common way. Okay. The response of the unknown should increase proportionally to the amount of the analyte added. So it should be increased proportionally. Okay. Okay, again here I want to mention here, right? I want to stress it out here. Here it's only show you 1, 2, 3, 4 is still not enough. You need to have at least 5 calibration points. So you need to have another flash, or the better way you need to have 6. So you need to have another flash. So here is just for an example. So it's not a very good practice to have just 4 calibration points. You need to at least 5 to 6 calibration points minimum. Okay, the response of the unknown should increase proportionally to the amount of analyte added. So as we increase the analyte, the response or the absorbance should increase proportionally. As the concentration increase, so as the absorbance reading. The gift of mathematical equation and graph for standard addition method. So when we plot, we will get a graph. The x-intercept of the graph is the initial concentration of the unknown. So we believe in the sample matrix already have our analyte. So the x-intercept where y equal to 0 is our concentration of the standard. The concentration of the unknown. So by doing this graph, you get this equation. You can obtain the concentration of the unknown. Okay, you can obtain the concentration of the unknown by looking at this graph, this point, or you can use this equation where y equal to 0. So you find x is what? Okay, if you do that, for example, in here you get 0.6463x equal to negative 1.8. Okay, x equal to, let me get my calculator, 1.6869 divided by 0.646. So you get negative 2.89. So you just need to change it to positive mark or positive symbols. So it will be 2.89 ppm. Okay, it will be 2.89 ppm. So if we compare with the external calibration method, okay, in the external calibration method, you find the adsorbent of the unknown and then you tally with the graph, or you can using this equation, you include the response here in the y and you will get the x value. Okay, that is in the normal of the external calibration method. But in this standard addition method, he is by looking at the x-intercept or y equal to 0. Why y equal to 0? Y equal to 0 is mean that there is no reading and we refer to the x-intercept. Okay, where x-intercept, of course, when y equal to 0. Y is 0. So that is the value of the concentration of our analyte in the unknown solution. But again, for example, you need, for example, in the future you need to perform the standard addition. For example, you get 2.89 ppm, right? 2.89 ppm. Okay, from this analysis. But you need to remember, previously we actually do the what we make as, okay, we dilute 2 mil of our sample in 10 mil, right? In 10 mil of flask. So we actually, okay, we add, here is 2 mil of our unknown solution, but you add with the 8 mil of solvent, right? Solvent. So totally it become 10 mil. So 10 mil divided by the initial volume 2 mil, so it is 5 time dilution. So your sample is already diluted 5 times. So whatever value you have here, you need to multiply by 5. Okay. For example, you add 1 mil and then you dilute until 10. So 10 over 1 become 10. So everything you add here, you need everything you get here, you need to multiply by 10. So you need to include the dilution factor. So if you're doing the standard addition using the normal method, so you need to include the dilution factor. Okay, if you don't calculate the dilution factor, you will not be able to get original or a true concentration amount of your analyte of interest. So you need to include the dilution factor. Okay. So I believe I need to add some here to determine the true concentration. Sample dilution factor must be final. Okay. So to determine the true concentration of unknown sample, okay, we already, from the graph we already get the initial concentration of the unknown. But to determine the true concentration of unknown sample here, because here is already diluted, right? Okay, so you need to include the dilution factor in the final calculation. For example, in the previous example, we maintain the amount of unknown solution is 2 mil, right? So 2 mil multiple by 2 mil, but you dilute to 10, right? 10 divided by 2 is 5 dilution factor. So for example, we calculated here about 2.89, right? 2.89 you must multiply by 5, okay, which is the dilution factor in this situation. Okay, so we will get the final or the true concentration of the unknown sample. So this is the important thing, the most important thing at the final calculation of the standard addition. If you forget about this, you will not get a final, or you will not get a true concentration of your sample. Later I save it first. Okay, the last calibration methods is the internal standard. For the external calibration method is the most commonly one we use. okay, when we are able to have a very good extraction method, that we can apply the external calibration method. But when we have the problem with the complex matrix, so you need to use the standard addition, because your extraction method is not able to remove the interference or remove the matrix effect. So you need to use the standard addition method. So the next one, this is the internal standard. Okay, when we need to use the internal standard, okay, internal standard is used to compensate deviation in measurement. In the other way is already described previously when we have the fluctuation in the instrumentation reading. Okay, so when we have that, so we need to use the internal standard. Internal standard, okay, same consideration is added to the range of standards to perform calibration curve. Okay, the same concentration also added to the sample for quantitative analysis. The intention is to obtain ratio peak area or height between the standard or sample and internal standard to compensate deviation in measurement. Okay, for example, you want to analyze Panadol or paracetamol. Okay, okay, so you get the peak. Okay, but when you run multiple times, suddenly it may reduce or maybe it become higher. So there is some fluctuation in the instrumentation. Okay, so when this happen, you need to use the internal standard. So you need to use the internal standard. Let's say here is the internal standard. Okay, here is the IS, here is the paracetamol. IS stand for internal standard. So let's say the instrumentation is fluctuate. So when the paracetamol reduce, same goes to the internal standard. The same internal standard will also will reduce. If the peak of the paracetamol is increasing, so as the internal standard. So the ratio between the paracetamol and the internal standard, or the ratio between the standard and the internal standard, should be the same. If even we have the problem of the standard, or even we have the problem with the fluctuation of the instrumentation reading. So if we encounter with the fluctuation of the instrumentation reading, so we need to use the internal standard, because the height ratio or the area ratio should be the same. Okay, even though we have the fluctuation reading. Okay. Okay. There is conditions for the internal standard. Okay, it must well separated from the components in the analyzed mixture. We already learn about the RS value, right? The RS value, as long the RS value more than 1.5, we should the internal standard can be accepted. So it must be well separated from the components. Internal standard must be stable and not react with the analyte. Of course, the internal standard must not react with the analyte. And the internal standard must have similar properties. The internal standard must has the similar properties to the analyte of interest. Okay, for example, the paracetamol is polar, the internal standard must be polar. The paracetamol, the boiling point is 300, the internal standard of the boiling point must be at about 280 to 320, or about the same. So the properties of the internal standard compared to the analyte of interest must be similar, not the same, but similar. Okay, so if you look over here, okay, okay, if you look here, okay, the blue one as the solvent. Okay, I forgot to put a legend, maybe you can put in your notes. The orange one here is your standard. Okay, and the internal standard is the red one. if we can see here, the amount of the internal standard, the red one is the same as I already mentioned here. Internal standard, same concentration, okay. So we need to maintain at the same concentration. For example, here is 5 ppm, 5 ppm, 5 ppm, 5 ppm. Again, for the calibration method, you need to use at 5 to 6 points, okay. 5 to 6 point of the calibration point. So this is not enough, only 4, right? So it just for teaching purposes only. So make sure in your research or in your dissertation you need to have 5 points of calibration. So here is the orange one is your standard of analyte. So you add, for example, 1 ppm, 2 ppm, 3 ppm, 4 ppm, and the blue one you add the solvent up to the mark. Okay, up to the mark. So you need to have the area concentration, you need to have need to determine the area ratio. Here, area of the standard, okay. You need to determine the area of the internal standard, and then you need to get the ratio. How to get the ratio? Just the area of the analyte divided by the area of the internal standard. For example, 1 over 2, 2 over 2, 3 over 2, 5 over 2. Okay, then you put in your calibration as the, so in the normal external calibration, here is you use the response, right? The response or peak area, and here is the concentration. But for the standard addition method, you need to use area ratio. So you need to find the area ratio. For example, the first concentration at 1 ppm of the analyte. So you need to calculate, okay, area of the analyte over by the area of the internal standard. For example, 1 over 2, 0.5. Okay. For example, here is 0.5. So 2 over 2 is 1. 2.5 over 2. What? 1.25. Okay. 5 over 2. So 2.5. So you put in the calibration curve on the response on the y-axis, and then you put the concentration at the x-axis. For example, the concentration of the here is, sorry, here, okay. So 1, 2, 3, 4, 5, for example, that is the concentration. So you plot and you will get the calibration curve. So you, okay, then we will get the R squared value 0.995. Oh, I forgot to mention you. Okay. So, okay, you know that, right? You know that why we need to use the internal standard is when we have the fluctuation reading. Okay. So what happened actually when we have the fluctuation reading? Oh, okay. Okay. What happened actually when we have the fluctuation reading? Okay. When we have the fluctuation reading is that, okay, for example, the problem with the fluctuation reading is sometimes you get the value high, sometimes you get the value low, or sometimes you get the value moderate. So when you plot the calibration curve, the R squared value, pretty sure it will get less than 0.995. So it will it cannot be accepted. Sorry, look over there. So the R squared value will be less than 0.995 if we have the fluctuation in instrumentation. Okay. So to compensate the fluctuation, so you need to use the peak area for peak area ratio, you know, area or height ratio. Okay. So you will get a very good R squared value. Okay. If you compare the normal method, they use just the absorbance of peak area. Okay. Okay. But if you don't have the problem with the fluctuation, it's okay. But if you have the problem with the fluctuation of the instrumentation reading, suddenly the peak become higher, suddenly the peak become low, or suddenly the peak become higher again, then you need to use the area or height ratio or using the internal standard calibration method to compensate this problem. Okay. If you for example, you perform the analysis of the complex matrix sample and you have the problem of the fluctuation as well. So you need to combine the internal standard method and also the standard edition. Okay, that is kind of the very tricky situation when you actually have the complex matrix, but at the same time you also encounter with the fluctuation of the instrumentation reading. So you need to combine the application of the internal standard and also the standard edition. Okay, pray for that never happen in your life. But in my case, I believe most all my student, not almost, mostly the analysis using gas chromatography will have that kind of problem. Okay, so I think that's it for the first introduction, for the first part of the chromatography, which is the introduction to chromatography. And so the next part we will look into the liquid chromatography, including the TLC, paper chromatography, and also HPLC. So until that times, if you have any kind of question, you can ask in the WhatsApp group. You can ask in the WhatsApp group, so we can share the information to everybody else. I believe I am not perfect as well. If I do make a mistake, please tell me so. We can discuss it in the group as well, so we can clarify if we have some thing that we not be able to understand. Okay, thank you very much. See you soon.